Ibuprofen. Hi students, welcome to this experiment 2, multi-step synthesis of ibuprofen. Second experiment in CM3291. Right, so you are supposed to make this molecule here as shown, 1 chiral center carboxylic acid from a multi-step synthesis. Hopefully you follow through these lectures and be very sure what to do before you embark into the lab. Ibuprofen is a well-known drug that possesses analgesic and antipyretic properties. It is particularly known for its use in pain relief from arthritis. Ibuprofen was discovered by Dr. Stuart Adams and his colleagues in the United Kingdom in the 1950s, patented in 1961, and first made available in 1969. It became available in the US in 1974. Ibuprofen tablets are sold under the trade name Advil and Motrin, and the chemical name for ibuprofen is 2,4-isobutylphenylpropanoic acid. Ibuprofen also has anti-inflammatory properties, and it belongs to a class of therapeutic agents such as non-steroidal anti-inflammatory drugs, or NSAIDs. Like aspirin and acetaminophen, ibuprofen works by inhibiting the activity of a class of enzymes called cyclooxygenase, or COX, COX. And these enzymes are significant because they catalyze the synthesis of prostaglandins, the molecules that have both positive and negative effects in the body. Prostaglandins are, for example, protective against the development of stomach ulcers, but they can also mediate inflammation. So you see that these ibuprofen products come in a wide range of forms, sold under different brand names. Okay, these forms include tablets, caplets, gels, sprays, liquids. And in some products, ibuprofen is combined with other ingredients. For example, it is sometimes combined with a decongestant, which is a type of medicine that provides a short relief for a blocked nose, and it is sold as a cold and flu remedy. So the synthesis and use of ibuprofen were both patented by Boots Pure Drug Company in the 1960s. Now the synthesis involves several steps and lead to the production of a considerable quantity of chemical waste. A more efficient procedure, which is shown in scheme 3, was later developed by BHC, which is a joint venture by Boots and Hurst Celanese. And this BHC procedure is now owned by BASF, the biggest chemical company coming from Germany, Ludwigshafen, and it's a model of atom economy, green chemistry technique. It was awarded the 1997 Presidential Green Chemistry Challenge Award given by the US Environmental Protection Agency, and this very green procedure is used as a BASF plant in Bishop, Texas, where about 7.7 million pounds of ibuprofen are produced each year. This represents about 20 to 25% of this world production of this very important pharmaceutical. But unfortunately, you know that this BHC procedure in scheme 3 is not suitable for the use in this lab. So to employ techniques and the reactions that we understand, we will choose to pursue the Grignard route, as described later part in the video. So your starting material for the whole multi-step synthesis will be p-isobutylacetophenone, a ketone. So first you can do a very simple reduction using a mild reducing agent, sodium borohydride, convert it to a secondary alcohol, and after that do a nucleophilic substitution using hydrochloric acid, concentrated form, to change it to the alkyl halide, after which addition of a magnesium to form the Grignard reagent, and after that you attack to electrophile carbon dioxide in the form of dry ice, and on acidification you get your product ibuprofen. Safety, very important, let me emphasize safety. Okay, you don't want to be the one getting caught in fire or be a live example of something unfortunate. So care should be taken to avoid inhalation, eye contact, or ingestion of any of the chemicals used in the experiment. So eye protection, nitrile gloves, and appropriate protective attire should be worn at all times. Sodium hydroxide, sodium borohydride, and hydrochloric acid are all corrosive in cases of skin contact. Okay, hydrochloric acid emits hydrogen chloride gas, which presents a serious inhalation hazard. Chloroform D and 1,2-dibromoethane are carcinogenic in cases of chronic exposure. Methanol, diethyl ether, THF, and 4-isobutyl acetophenone are flammable. THF tends to form peroxides more readily than diethyl ether, and these peroxides are very explosive. So please take care of all this in the lab. Do not have any pranks. Please adhere to the safety rules. Okay, right. I'm going to give you some tips on this synthesis and some of the experience, I would say, that was done by people who have tried this experiment so that you don't have so many hiccups. So number one, I will encourage you to do it in more than one batch. That means at least 2 or 3 batches, just in case that something goes wrong. I'm sure all of you knows about the Murphy's Law. When something goes wrong, it can really go that wrong. Okay? So suppose I'm going to give you this amount of materials, and I would say that maybe proportion in such a way that you can do it at least 2 or 3 batches. Okay, maybe the first time is a trial, just like in titration in some experiment. The first time you just do it in a more carefree manner, maybe just to test to see the environment, how's it like, how familiar you are with the kind of setup and reactions. Okay, of course I don't have to impose on you. You can do it one batch. It's perfectly fine, but you should listen up. Now, if you want to do it one batch, be careful, because the experimental procedure is based on the certain amount given in the lab manual. You can't just say that I give you 5 times of that and everything multiplied by 5 without thinking that the capacity of the glassware is unable to cope with it. So you have to plan first and see, whether you are able to do that when you scale up in that manner. So suppose the solvent is not able to be stored in the 250 ml round bottom flask. What do? You add a bit less solvent, but with more reagents. How does it affect the reaction rate? You remember collision theory? So you're having a higher concentration, molecules bombard at a faster rate, you have more chances of effective collision frequency, right? Which means to say that the temperature, if you heat it up as the same as the part where you don't scale up, your reaction may go what we call a runaway reaction. That means it's too vigorous, too much heat generated, and it could get explosive and you can't really control it. So that's why, to be very safe, please follow the experimental procedure. Okay, next thing, because it is a multi-step synthesis, you encounter several intermediates. Now, they are not the most stable thing. I'm not saying they're unstable, but they are not as stable as a product or reactant, Okay. Your intermediates are crucial to the next step and subsequently the final product. So always dry your intermediates. If you need to, blow nitrogen gas through it, vaporize all the moisture, solvent, whatever you can do, and seal them tightly with paraffin, paraffin film, okay, at the neck of the round bottom flask. And then you put the stopcock, okay, or you can store inside a vial, which is more preferred in fact, because of a vial is rather small, it's more compact, and you have less chance to store other vapor. Okay, again, paraffin it, store in low temperature. If there's a freezer, store in the freezer. If there isn't a freezer, store in the fridge. Your lab officers will guide you. Okay. Now coming to the experiments, so once again I have to remind you that this specific amount, we mention it at the start of the lab. Okay, you are being limited by this ketone here, so marks will be deducted for sure if you ask for more of this ketone, because we really give you more than enough. Okay, and inside the lab manual, all the steps are assumed to be 100% yield. What I mean is, if you take a look at the lab manual, the first step says dissolve 3 ml of the p-isobutyl acetophenone. Okay, and then in the next step, to make the next intermediate called 1-chloro-1,4-isobutyl ethane. This is assuming that what we got from the first step is 100% U. Okay? Take note of that. Which means to say that the next step, when you are doing the Grignard reaction, the 1.0 gram of oven-dried magnesium, once again, is based on 100% U of the second step and of the first step. Okay? Right, so once again, 1.0 grams of the oven-dried magnesium, 0.75 ml of the 1-chloro-1,4-isobutylphenyl ethane is based on the fact that you make this compound from 3 ml of the ketone, 100%. Okay. Step 1. Dissolve this ketone in 9 ml of methanol in a separatory funnel. Methanol, is not very safe. Just don't drink it, okay? Please don't drink it. Do insert the fume hood, weigh out 0.75 grams of sodium borohydride, and then quickly add it to the separating funnel. So we are doing this reaction not in the traditional round bottom flask or conical flask. We can just do it inside the separatory funnel, because after that we're going to do some extraction, so we save time and effort, make it less cumbersome, don't have to transfer here and there, clean more glasswares, and also you may lose some U, and allow it to sit for 10 minutes. Now, lab manual says 10 minutes. These are the numbers that you should be judgmental when you're doing the reactions in the lab, because it's not 10 minutes, okay, time's up, I'll stop it and go. You have to monitor reactions. Some reactions finish slightly under 10, some will take more time. It really depends. It's not like everybody will just nice 10 minutes and you get a high U, okay? Next, add 30 ml of this 10% HCl. It is corrosive, beware. And then extract the product from the mixture using 3 portions of 15 ml of diethyl ether. Ether, the smell is not so favorable. So please don't take out your separatory funnel and do the shaking outside here. Please, I don't want to see any of these. Remove the solvent by rotovap from a 50 ml round bottom flask. Okay, so in the video, you see that I'm going to show you what's going to happen. Place 1 drop of the product in NMR tube, because we want to do a scan to see how pure is the product. Here we are not doing any purification, but it's more like a gauge. You see your NMR spectrum, you can decide which peaks are for your product. Then if there's any that belongs to your reactant, so you can measure the relative intensity and you can make a gauge and estimate how good was your reaction. Okay, at 0.6 to 0.8 ml CDCl3, this number is crucial. Too much, too dilute, the spectrum doesn't appear good. Too little is too concentrated. The lab officers may not want to do it for you. Okay, so you must have the right spot. Record the product NMR, and of course you're gonna put this down in your lab report. Next intermediate, 1-chloro-1,4-isobutylphenyl ethane. So using this pastel pipette, carefully transfer the previous compound into a separatory funnel. Okay, now use 2 portions of concentrated HCl. Look at that. It is 12 molar. Look at that. 12 molar. This is mole per dm cube. You don't want to get your skin in contact with these, okay? Trust me, it hurts really bad. Always put your gloves on, and do not roll up your sleeve when doing that. I know some of you think that rolling up your sleeve, right, you can maneuver the glassware better, but no, okay? Can't do that. You hurt yourself. And then flush it down, all the remaining, into the flask in the pipette. Shake it for 2 minutes. Okay, shake it. You notice that there'll be some fumes and gases coming out. So intermittently try to vent it, okay? You don't want to have a lot of pressurization inside your reaction setup and booms. Explosion. Okay. Extract this product from the mixture with 3 times of 15 ml, same solvent, diethyl ether, and then dry with sodium sulfate anhydrous. So it's the same step you did in year 2, extraction and drying agent. Remove the solvent by rotovap again. Okay, again, many students forget to weigh the dry 50 ml RBF. So after they add it in, they do the rotovap, come out, yeah, I got it. Hey, what's the U? Then you're going to say, I forgot to take down the weight of my empty RBF. So they got to take a new dry RBF, weigh it, and then transfer everything down. And because you know that there's some remnants there, so they use some of the solvent, wash it down again. So that'll be double work. Who wants to do double work? It's not fun, man. Okay, and now you're done with this reaction. So once again, you can record the NMR. Place 1 drop of this into NMR tube and add the appropriate amount of CTCl3. Okay. For this step, the NMR is not compulsory. What is crucial for this experiment is the 2 NMR. One for step 1, when you do the reduction of your ketone. The other time will be for the NMR of your final compound, because we really want to check the purity. Next step, there will be a Grignard reactions. So the setup is as such. So warning, we should conduct this procedure in nitrogen atmosphere. The setup is here shown on the right side. You have a bubbler, the oil here, nitrogen gas going in. Make sure it's always on because we want an inert atmosphere. We know that Grignard reagents is very hygroscopic, and any moisture can just decompose it. This is a condenser. Water in from the bottom, water out. Don't mix it up, okay? 2 net RBF. For this speed, right, you can try to adjust it until you get the right spot again. About 1 bubble per 5 seconds. So after you're done, add 1 gram of oven dried magnesium. Again, when you have the nitrogen going in, okay, so that it be everywhere. Then you add the Mg inside, okay, and then 0.75 ml of the previous intermediate. Add your solvent THF, 5 drops of 1,2-dibromoethane. Think about why we add this reagent. Why 5 drops? Is it really a reagent? Is it a catalyst? What does it do? It's good that you do some research here. Make sure that the liquid reactants are added using a needle through the rubber septum. So you see this part? Rubber septum. You got to fold it. It is secure. Nitrogen going in. Any liquid, right? You puncture the hole using a needle. Be careful. You're handling needles, okay? So suppose this is a needle. You put it in, right? How do you open the needle? You uncap it by doing this, okay? Observe the surrounding first. Make sure there's nobody. Okay, this is inside film hood. Suppose your hands are inside film hood. Then you just make sure you open it. Okay, no recoil. Don't try to control it because some people like to control it and that you get the punctured skin. Not funny. You say, ouch. Then after that, you can begin heating under reflux. Monitor the temperature. Make sure that it's just nice reflux. Okay, so research on the boiling point of THF. Ask yourself, what temperature will THF boil? Then you decide, do I use a oil bath or a water bath? So how do you know that the Grignard reaction is starting? Okay, you see a lot of foaming, like really white foams. Come out of white foams when somebody gets super wasted after drinking so much liquor. Bubbling come out, okay, and after that you don't stop it. You know, this is just like the beginning of the reactions. Then you heat it under reflux for about half an hour. You can choose to go for lunch. It's completely up to you, or you can stay and monitor the reactions. After that, cool the reaction mixture using a water bath. Don't use ice bath, okay? You crack and then you just lose everything. I also can't help you in that. Disassemble the apparatus, okay? And still at this stage, you should keep the nitrogen gas on. okay, because we haven't used the Grignard reagents yet. Now at this point, you bubble about 1 liter of CO2 into the reaction mixture. So here in the lab, either we'll be using dry ice, or we'll be using a gas cylinder with CO2. So it depends on which day you are, on the availability of the materials. You may get different versions of CO2. Now if you get dry ice, what you do is, I will demonstrate in the class, it's an improvised method. You put some dry ice inside this Buchner funnel, okay, then the exit here, the side exit of the Buchner funnel, you use a orange tubing, okay, connect it to a plaster pipette, okay, make sure it's connected, no loose gap. Insert it into your Grignard reagent, and after that, make sure everything is clamped, okay, to your retort stand so that it doesn't topple. Then you add slowly some hexane into the Buchner funnel, and we know that because CO2 prefer to be in the gaseous state. You learn from the phase diagram of CO2. At RTP, it is CO2 gaseous. So now you are forcing it under high pressure to CO2 dry ice. Of course, when you add any liquid, it will just sublime quickly, okay? So you put your hand on top because you want to transfer all the CO2 into your reaction mixture, and if it feels a bit cold, okay, just put your hand out a bit and put it in again, okay, intermittently. Don't worry, I will demo in the class in the lab. Bulb it for about a minute or so, then decant the solution into a separating funnel. Use the ether again, rinse the flask, the mg. You should have excess magnesium. Then decant all the ether solution in a separating funnel. Okay, add the acid and mix. Think about why we add HCl. Okay, I have to think. Then after that, you remove the organic phase and let it stand. Extract this aqueous phase. You watch it carefully. This part is quite confusing because you have many extractions here. You have to do the right thing. If not, you just throw away your compounds. Always play safe if you're not sure or you're just paranoid. After extraction, the conical flask you just place aside, label using a marker. Sekali you forget is it aqueous or organic. Okay, of course you can sniff, but it's not healthy. Put one side, label everything until you're done with everything. You're really sure that you get your compound. You can discard the rest into the appropriate waste container, and a chlorinated, non-chlorinated aqueous. So extract the aqueous phase with 2 times 15 ml ether. Combine the organic layer and extract again. You see, combine the organic layer, extract this with NaOH, a base. Just now with an acid, now with the base. What's going on? Again, you need to think, okay? It's not that hard as it seems. Then, acidify the aqueous phase by adding an acid HCl. Use the limits of pH paper to make sure it's acidic. Then you have to do this. Still here. Then, to this aqueous layer, you extract again using ether, and after that you dry with sodium sulfate. So this is like the final part. So go through these 2 parts again and do not be confused. Okay. Remove the solvent by rotovap to get a product, and of course pre-weigh it first. After that you pass a gentle stream of air, okay, to remove the last trace of the solvent. Okay. What you can do here alternatively is you can actually connect it into the vacuum pump, but careful, you don't want to remove all your compounds. So slowly turn on the turn on the vacuum so that you can vaporize any solvents that's left behind. Okay. After doing so, you place 1 drop of this product into NMR tube. You do an NMR analysis. This is the one that everybody must do, just like the first step. Okay. Right. This is for your own. We are doing a proton NMR for individual analysis. Then for some of you who don't get very high yield, you can actually combine with your friends and place about 200 mg. This is more than what you need for a proton NMR because we're scanning carbon. Why do we need much more product to scan carbon NMR? It's all about the isotopic abundance, because the only carbon NMR that's active in the machine is carbon-13, and you know the carbon-13 is less than 1% abundance, so we need more of the sample to compensate for this low isotopic abundance. Okay, and your lab officers record a 2-dimension NMR proton against carbon, so you can see the cross coupling between the carbon atoms and the hydrogen atoms. It's really interesting. Let me talk about mechanism of these reactions. In organic chemistry, whenever you do a synthesis, you can't do away with the mechanism. So here, in the first step, we know that sodium borohydride reduce the ketone by what kind of reaction? Recall. This is a nucleophile, right? Nucleophile attack the electrophile, nucleophilic addition first, open up the pi bond, you get O-, after that work up, you get a alcohol. Because this carbon is sp2 hybridized, is trigonoplanar, so your product, even though it's chiral, it could be a racemic mixture. Let me just say, it could be, not must be. Some people, they wonder, they thought, if any time I begin with a planar structure and the reaction site is on the carbon or on the atom that's planar, even if my product has a chiral center, is going to be optically inactive. This is not correct. Because you assume that the nucleophile has equal probability of attacking from the top and the bottom, right? So it should be 50-50. But in reality, we know that sometimes reactions are biased due to temperature, movement, so we can't predict. It's like you flip a coin, a fair coin that's not loaded, 10 times. We expect to be 5-5, right? No, it doesn't happen that way. It may be 4-6 or 3-7. Then what, you say the coin is biased? No, okay? Only if you do it many times, then the percentage becomes almost 50. So just like this case, I won't expect my final product here of this alcohol to be racemic. Okay, very unlikely. Not saying it's impossible though. Next step, this is a nucleophilic substitution. Protonate the hydroxyl group, making a better leaving group. Chloride attack from behind, kick it out, and goes in. You get a halogenal derivative. Next step, addition of Mg is squeezed inside between the two non-metal, carbon, chlorine, creating a very reactive intermediate. Then here you add CO2, which is an electrophile. Okay, this is mechanism. This bond, which is semi-covalent and ionic, full of electrons, attack the carbon. This electron deficient because of the 2 oxygen that polarize this bond. Break the pi bond, push to the O gets negative charge, counter ion is Mgx plus, you stabilize it for a while, and that's why you add the acid, so that you can protonate the conjugate base of the final carboxylic acid. You get back this COOH. Okay, so here are some little extras for you. So I will show you in the mechanism, right, that you form the Grignard reagent. Did anybody think of any possible side products that could be formed? Okay. Now this is where it comes in handy if in the future you are going to perform any organic synthesis. Notice that this Grignard reagent could attack itself again and form the dimer. Do you notice? It's because the benzylic and allylic halides are reactive enough to react easily with this Grignard reagent. So that means it can react with itself again to form the same thing, right? So how can we minimize this? How can we minimize this issue of dimerization? We totally don't want it to happen. One way that we can do is we use THF as a solvent instead of diethyl ether. Okay, what do we call this kind of reaction besides dimerization? Self-coupling. Okay, any dimer that is formed will be removed by the THF. How come? It's possible because the sodium salt of ibuprofen is soluble in water, but not ether, whereas the dimer is soluble in ether, but not in water. You can see easily because the dimer is very hydrophobic. There isn't any interaction with water, ion dipole, or even Coulombic attractions. No. So that's why we use THF. I'm going to give you the very nice NMR spectrum, proton NMR of the starting material and all the rest of the intermediates. Because in the end, you're going to do a 2D NMR, okay, as a team. I don't want you to see such a complex 2D NMR and then you like goes what we call people and goes like chua, and then after that some people just give and say swala. Is that how they say it? Anyway, this is a perfect proton NMR spectrum of the ketone. Okay, the integration shows that what are the protons that are responsible for these signals. Recall this is the TMS, 0 ppm, high fill. Okay, this is down fill, up fill, high fill, low fill, deshielded, shielded. Okay, ratio is 2 to what's this? 5, 1, 6. So if you can count 3, 4, 2, 1, 6. Please go back and do some matching, not using this spectrum because this is the one I give you. It is a reference. You should do it onto your own NMR spectrum. Next intermediate, the alcohol. Okay, you see a change here. 4, 4, 1, 2, 1, 1, 3, 6. Again, you can do some conclusion here. The chloro compound. Okay, try to compare subtle differences. Okay, but you can really see something that you can talk about to tell me in your report what is the success of your synthesis here. And lastly, your final target molecule, ibuprofen. A bit more complex, but this is a very clean NMR sheet. Okay, I really hope that most of you get this. Okay, this is my dream, which I think can be realized. Okay. Finally, for analysis and discussion, you have to show your experimental observations. So I always emphasize that when you're doing any lab, have a logbook, you record down any small observations, anything you see, just record. Okay, alright, just record. Maybe you say that, oh, somebody tapped me and called me for a while. You just record all these little things. The sky is very bright today. There's haze today. I can't breathe. I need to wear N95. All these are like a journal, like a diary that you can look back and record the day. These are the things that help you remember what you did on that day. People will just put, okay, the color change from yellow to brown, black pupil evolve, and you see effervescence scene. These are things that could be repeated for the same synthesis, but what's different is the friends around you, the day itself, the weather, all this. Maybe you take a cup of cappuccino in between the break. This helps our mind to recall what happened the day if you're trying to do that report. Okay, so make sure you calculate the yield of every major steps. Even though it's just crude yield, you might have to calculate. And of course, you have to include the overall yield of the synthesis. Overall yield means you take the final ibuprofen that you got over the theoretical ibuprofen you got from that particular starting material, ketone. In your proton NMR spectrum, you have to ID the presence or the absence of the peaks that tell you whether your synthesis has gone through smoothly. And finally, in your two-dimensional NMR, you have to explain what are the signals and why is that so. Okay, get your hands dirty. Summarize it in a table. We will appreciate this. Being neat. Okay, present your data in a very proper manner. Okay, so you see that in this synthesis of ibuprofen, we teach you how to make a drug. But like I said, this is not Breaking Bad. Next time when you invent something, some drug, you can actually add some dye, those harmless dye that make it very fanciful, so that you can win over your competitors. Something that's pink color or blue color, okay? But here I'm not teaching you to make drugs. It's just a good way to relate what we learn in chemistry to some kind of a social media or any shows that we have seen. I guess it's more interesting that way, right? I will talk about the recrystallization, the resolution of the ibuprofen salts, and also using the polarimeter in 2 separate videos. So for now, read through a lab manual, do some research, think about what's going to happen, plan your synthesis well first, okay? And I'll see you in the lab. Bye.